Hello everyone, welcome to my video. We are starting chapter 5 in this video, beginning with rotation. So far, we have looked at displacement, velocity, acceleration. Most of our analysis were under the simplification of treating the object as a particle. However, this type of simplification cannot always be used. When needed, rotational motion must be included in our analysis. For example, we want to closely examine the trajectory of the projectile motion, or we want to see in the example on the right how the range is going to hit. In the meantime, many things will remain the same. In rigid body motion analysis, such as our previously learned concepts, still hold, most of them, or all of them, but just will be applied in a much more complicated scenarios. Rigid body is defined as a system of particles where the distance between the particles remain unchanged. But in reality, no object is absolutely rigid. All solid materials will change shape to some extent. Therefore, it is just a matter of what our interest is. Are we interested in a flight path from A to B, or are we interested in how hard the wing is going to flutter? Right? In this course, we will make the assumption to treat all materials as a rigid body. So, a little bit simpler. In plane motion, or 2D motion, all motions can be summarized into 4 categories, but I would actually say there are only 3. Rectilinear and curvilinear translation can be summed together as they are motion of the body can be represented by any single point within the body, and all particles or points within the body moves in parallel in the same way. Then, fixed axis rotation in this case, all particles not on the axis rotates or moves at the same angle in the same time period. Lastly, the complex motion. All particles within the body moves differently, but later on, when we study them closely, such as the pen in my hand, the complex motion is actually just a combination of translation and rotation. We will start with the rotation here. Using this gear as an example, any line on this gear will have 3 same parameters when it rotates. They have the same angular displacement, they have the same angular velocity, they have the same angular acceleration. Then, these basic circular motion equation can be applied here. We can calculate omega, we can calculate alpha, we can calculate we can use the omega d, omega equals to alpha d theta. If these equations are a bit overwhelming at the beginning right now, let me help you with some tips on the next page. Angular motion has many similarities to rectilinear motion from the equation perspective. We'll start with looking at the velocity here. For linear motion, velocity is ds over dt, and then for angular velocity, that is d theta over dt. In linear motion, you're traveling in a distance s, and in angular motion, you're traveling by an angle theta. You see how s and theta are related? Then acceleration. For linear motion, we have dv over dt, but for angular acceleration, they don't have v, they have omega. It's d omega over dt, and a, the letter changes to alpha, representing the angular acceleration. As for displacement, they are similar as well. For displacement, we have ADS equals to VdV for rectilinear motion, and for angular displacement, we have alpha d theta equals to omega d omega. Right? A replaced with alpha, S replaced with theta, V replaced with omega from rectilinear motion to angular motion. Lastly, all these equations we derived for linear motion can be modified by changing V to omega, A to alpha, and S to theta, and applied in angular motion. To study fixed axis rotation, we need to use the NT coordinate system. The fixed point O is naturally the center of the curvature, which will give us the radius r. Then everything can be calculated accordingly. V equals to r omega, the tangential acceleration is r alpha, and the normal acceleration is r omega square, or v squared over r. And this v here is the tangential velocity. That's how tangential velocity and normal acceleration is related. We can also do this in vector form. The direction of them will be given by the right-hand rule because we're doing the cross product. V is omega cross r. An is omega cross r. We'll do the inside bracket first, and at is alpha cross r. Be careful. The order matters. It's omega cross r, not the other way. Otherwise, you will end up with the wrong direction. Since we're doing the cross product, please be careful about the direction, using your right-hand rule properly as needed. There are some tips I would like to give you when solving fixed axis rotations. One is if objects or point of interest is on the same bigger object or a wheel, as shown on the example on the right-hand side, they will have the same angular velocity and the same angular acceleration, because they can be treated essentially as a single object. For example, on the right-hand side, BC, omega B equals to omega C, and alpha B equals to alpha C, because they are on the same axis. Right? On the same object, same omega, same alpha. When two rotating bodies are in contact with each other, most of the time are gears, such as on the right-hand side example, A with B, C with D. At the contacting surface or contacting point, they will have the same tangential velocity and tangential acceleration. For example, here we have VA equals to VB at the contact, VC equals to VD. They're all tangential velocity. And the acceleration, the tangential acceleration of A equals to tangential acceleration of B. We also have ATC equals to AT of D. All right, welcome to Chapter 5. Take a look at these recommended readings. Thanks for watching. I'll see you next time.